In this video, I want to go into more detail about parametrizing policies in the context of reinforcement learning. So here's your usual Gaussian policy. So what you'd say is, all right, so we are in a certain state and we want to make a decision about which action to make. So how to do that? Well, the first thing we do is we convert S into some kind of feature vector phi of S. Now, if S already happens to be a vector of numbers, you could just make phi be the identity. Or you could make phi be extremely complicated, like it could be a neural network that's extracting interesting features from the state S. Anyhow, once you've extracted this fixed length vector from the state S, what you can do is you can say, all right, let's compute the dot product of that with our parameters theta. And basically, that's going to be our action. Now, we do want to introduce some kind of randomness into the action selection process, for example, in order to do more exploration. There is other justifications as well. So what we'll do is, instead of saying, well, this is our continuous action, what we'll say is, well, our action is going to be normally distributed around this guy, right? So that's basically going to be it, but that's just going to be the mean of the possible actions. And there's going to be some variance sigma squared there. All right, so what we're doing is we're essentially saying, well, depending on the state, we'll have a different phi of S. And then, depending on the parameters theta, we're going to select a mean for the A. And then, well, there's a little bit of noise in the process of selecting the action A. So actually, A, if sigma squared is large especially, could be pretty far away from this mean of the action. Okay. So in this case, what we're saying is that A is going to be, basically a real number, conceivably any kind of real number, although probably it's going to be a real number somewhere around this. And depending on the state, it's going to be different. So, okay, that's your basic Gaussian policy. Now, like we said, this phi of S, it could be arbitrarily complicated. It could be any sort of function that takes S to a vector that's the same dimensionality as the theta. So one thing you might say is, well, hey, why do it like this? What you can do is you can just say, well, A is going to be normally distributed around some mean. So around some mean, that's going to be just f theta of S with this variance. So that's just making things a little bit more general. This is saying, well, f is going to be, for example, some kind of neural network that takes in as input the state S and is parameterized by the weights theta, and it produces a mean for the action. So that's going to be a generalization of the Gaussian policy. Now, another thing you can do is you can say, okay, well, suppose that my actions are not real numbers. Suppose that I can only have two actions, for example, push to the right and push to the left. That's the case with cart pull. So how's that going to work? A can't anymore be normally distributed because A is not a real number. A is either 0 or 1. So what can you do in this case? Well, what you can do is you can say, well, if A is either 0 or 1, it looks like A is Bernoulli distributed, right? So what you can say is that A is going to be Bernoulli of, again, some kind of function that's parameterized by theta of S. And that's that. So that means that A is going to be 0 with probability 1 minus this, and it's going to be equal to 1 with probability f theta of S. All right. So that requires it to be the case that f theta of S is actually a number that's between 0 and 1, right? Now, we do know how to produce those kinds of things. So if you have a softmax function with two possible outputs, it's going to produce basically f theta of s and 1 minus f theta of s. So how would that work? Well, one thing that you might do is you might say, all right, so A should be like that. So we'll have a little neural network where here we have a softmax, and here we'll have two outputs. And here we'll have the inputs x. And those could be just fully connected. So in this case, this will be s, and this will be the outputs. So that could work. Now, again, what does A is Bernoulli f theta of s mean? Well, it means that probability of A equals 1 is just equal to f theta of s. Probability of A equals 0 is equal to 1 minus f theta of s. And f theta of s, you could just read off one of the outputs of the softmax.